Greetings, I'm Professor Tajiroglu of UCLA, and this lecture is intended for students taking the class cee103, Applied Numerical Analysis and Modeling. If you're not one of those students who are registered for this class, please stop watching this video because it contains some copyrighted materials. The topic of this presentation is partial differential equations, and let's start with some nomenclature. I'm going to talk about PDEs, and I'm going to contrast them to ODEs, the ordinary differential equations. Partial differential equations involve, unlike ODEs, derivatives with respect to more than just one independent variable. And in our context, those independent variables will be typically space variables like x, y, and z, or time variable t. So here's a second-order linear ODE that describes the motion of a mass that is attached to a rigid boundary with a spring and a dashpot. In the equation you see, the first term denotes the inertial forces in the system, mass times acceleration, which is the second derivative of the horizontal displacement with respect to time. The second term denotes the force generated inside the dashpot that is countering the motion always, with magnitude c times the velocity, so it's proportional to velocity, and c is the viscous damping coefficient. And ku denotes the force inside the spring, again, that is countering the motion of the mass. And f, finally, is the external force. Here, the field variable is u, the horizontal displacement of the mass, and it is only a function of time. It is not a function of any other variable. Therefore, all the derivatives that are appearing in here are full total derivatives. And the highest order derivative that appears in this equation is the second order derivative, therefore the name second order ordinary differential equation. And finally, this differential equation is a linear differential equation because its differential operator satisfies, as we have described in class before, the additivity and the homogeneity properties. Here's another differential equation. This one is a partial differential equation, which is the advection equation. It's a hyperbolic linear PDE that describes the transport of a chemical inside a fluid. So the free field variable is that u, and it is a function of both space and time, x and t. And as you can see, there are derivatives appearing in this equation with respect to both of those free variables. So this is a PDE, and its solution will require more than what we have done for ODEs. As ODEs, PDEs will also involve initial and boundary values. So we have either boundary value problems where the field variable's value on a certain range of the domain is prescribed at initial time or some reference time, such as time equals 0, as it is in this red box. Or we will be dealing with initial boundary value problems where the value of the field variable is prescribed on a portion of the domain along the spatial coordinate and at all times. Equation and boundary data in the case of a partial differential equation may be defined over an irregular domain in space. So those kinds of things will complicate the solution of the PDEs. In this class, for simplicity, we will only deal with single PDEs as opposed to a system of several PDEs. And also for simplicity, we will only deal with two independent variables. So we're going to have either spatial variables like x and y at the same time, or one space variable such as x and one time variable denoted by t. And we will sometimes denote our partial derivatives with subscripts as a shorthand as follows. So here you see in the green box the partial derivative of u with respect to t, and it is simply denoted as u sub t. Likewise, here's a cross derivative, a second order derivative of u with respect to x and y, and we denote it simply as u sub xy. So here's an example ODE. This is the advection equation, which we have seen before. It is partial of u with respect to t equals to negative eta times the partial of u with respect to x. It describes, for example, the evolution of the concentration of a chemical in a transporting liquid, or evolution of some other conservative property such as heat in a heat conducting domain. Its unique solution will have to be determined also through an initial condition. So you need to have the equation in the blue box, which is the governing equation, and it has to be appended with an initial condition, such as the one in the red box. So in this particular case, the value of u is being prescribed at a reference time, such as time equals 0, over a range of x values. And in our case, the problem involves, in this particular example, the problem involves an open domain. So x ranges, say, from -infinity to +infinity. And with these two pieces of information, we are seeking a solution, u of x of and t, for all times, including and beyond the initial time, at all x's that make up our domain. So what is the value of u that satisfies both those equations? An analytical solution is possible for this simple problem, and we will seek that. So we're going to be talking about now the method of characteristics, which is going to allow us to get a solution to this problem. We're going to start by finding the curves in the xt plane, the space-time plane, along which the field variable u is a constant, and you will see why this is going to be a fruitful approach to this problem eventually. So here's my space-time plane, x and t, and I am trying to find a curve whose functional form I do not yet know, and I want to find this curve such that it's the value of the field variable u is a constant along that curve. So let's just denote some generic curve like this, yellow curve like that, which is parameterized by some scalar r. So r is like the little tick marks on a tape measure, if you will, and it tells you where along the curve you are. Okay, and our goal was to find well, we can also describe the same curve in canonical form as a g of x and t equals to 0. Okay, so the functional form of this curve can be also expressed as a function of x and t. And since r, every tick mark along this yellow curve will correspond to a unique x and t, that means x and t both can be parameterized with respect to r along that curve. So we can rewrite that g as a g of x of r and a t of r, which can be summarily denoted as g tilde of r equals to 0. So it's still the same curve. We have its representation with respect to r explicitly or implicitly with respect to x and t, which depend upon r themselves. So let's just start out with the first condition, which was the fact that the variation of u along this yellow curve was equal to 0. So that means that its total derivative, the total derivative of the field variable u with respect to r, must be equal to 0. And since u is a function of both x and t, we can use the chain rule and rewrite that expression as partial of u with respect to t and the derivative of t with respect to r plus the partial of u with respect to x and the derivative of x with respect to r. And we can then utilize our governing equation in the blue box, and where we see a partial of u with respect to t, we can insert negative eta times the partial of u with respect to x. So our equation still holds. So let's just hold this on one side. Well, before we hold it, we can actually do a simplification. We can eliminate the partial of u with respect to x from both sides of this equation and rewrite it as follows. So now we have this expression. This expression is embodied with the fact that the field variable is a constant along this yellow curve, and itself, the field variable, is obeying the equation in this blue box. So all of that information is embedded in this equation that we have. And now I'm going to do something else. I'm going to observe the fact that this function that represents the yellow curve g is also a constant, right, in its canonical form, g tilde of r is equal to 0, which is a constant. So I can evaluate its derivative with respect to r. That derivative, the derivative of g tilde with respect to r, must be also equal to 0. And again, I can use the alternative expression for g, which was the g of x of r and t of r, and use the partial derivatives and the chain rule to represent that total derivative of g tilde with respect to r in the following form. And now I have two sets of equations. One set denotes just the total derivative of a curve, and then the other set denotes the fact that u obeys this governing equation, plus along this curve it is a constant. And I notice that this term, dt dr and dt dr, is common to both. And then the other term, dx dr, is also common to both. And they're both equal to zeros. That means the partial of g with respect to t must be equal to eta, which both multiply dt dr. And also the partial of g with respect to x is equal to 1, which both multiply dx dr. And then this allows me to determine what the functional form of g is. It is very simple. It must be equal to g must be equal to x minus eta t. If you want to check it out, well, just evaluate the partial of this result with respect to x and you're going to get 1. And evaluate the partial of this result with respect to t and you're going to get negative eta. And this is a unique solution, but it's not a complete solution. In fact, you can add a constant to this term, and if your g was as follows, that it was x minus eta t plus c, it would still satisfy the equations in the blue box. So we have found this g along which this field variable u is a constant. And what does it look like? Well, it looks exactly like a line. It is a line. In fact, it is a family of lines, all of which have a slope of eta along in the xt plane. So that's very revealing because it tells us the solution to the equation in the blue box. Okay, so here's the replaced version of that unknown curve. We now know it's a line, and we can just evaluate it for a particular value of that constant x naught, and it will look like this. But then any kind of line that has the same slope with a different intersection constant will satisfy the equations here of g. So it's just a family of lines that will satisfy this equation. So now let us recall the initial condition we had for our advection problem. The initial condition was that at time equals to 0, t equals to 0, so that's a little typo. This t should be replaced with a 0. U of x comma 0 is equal to u naught of x. So it is defined for the entire domain of x's at initial time with this given function of u sub 0. So this function u sub 0 is known to us. And now we can plot that. So let's plot that initial condition in a three-dimensional plot. The horizontal axis is x. The t-axis is drawn in perspective like that, and then the vertical axis is our field variable, u of x and t. So if I plot that initial time along all x's, let's say that the initial condition looks like this sort of bubble function, if you will, it is going to look like that. At time t equals to 0, it will have been completely defined. So our goal in our attempt to solve this problem is to determine the values of u of xt for all other times beyond this initial time. And our method of characteristics incursion told us that there are these lines with a certain slope, eta in particular, along which the solution will remain a constant. So this implies that the solution in the next time, the time that follows time equals to t0, will be a mere translated version of this initial shape, u sub 0 of x. Right. So let's just mark, for example, one particular spot. Let's just pick this peak of our initial condition. I mean, this is just an example, but let's just pick a characteristic location. And that means that the solution at all other times this peak at all other times will be along this line. It will be translated by the slope dictated by that line. And of course, the same thing is valid for any other point that we can mark on that initial curve. So that means that initial curve entirely will be translated in the space-time domain along a slope. And that slope is obviously dictated by the value of this eta, which is a characteristic variable for this advection problem. So what's happening here is that imagine that this is the concentration of a chemical in a one-dimensional river. And over time, we are trying to take a look at what this concentration will look like along our river. And in the initial time instant, we are given a snapshot of that initial condition of this concentration of this chemical. And then the river has a certain velocity, which is related to this eta ultimately. And then what that river will do is it's going to transport this chemical along its path. And of course, at all other times, this shape is going to look like this. And this is an advection equation. And there are also other equations that describe phenomena like this, such as the advection diffusion equation. And if you were looking at an advection diffusion equation, we'll have additional terms in the governing equation. And then the solution to that will not be this constant translation of this initial shape, but it's also diffusion along the positive and negative x directions. So that would be a more complex phenomenon, but a partial differential equation that describes it exists nonetheless. Okay, so that said, that sort of geometric intuitive explanation said, we can just write down the algebraic expression for what u of x of t is at all times, and it will be equal to u sub 0 of a translated coordinate of a scalar value, which is x minus eta t, right? Which is actually none other than our g tilde of r function itself. It's the canonical formula for that line r. So it perfectly describes the value of our field variable at any location at any time. So we have actually solved this problem. It actually satisfies our initial condition as well. Okay, so now let's talk about the classification of PDEs. And we are going to get our nomenclature for classification of PDEs from another field of mathematics, which is geometry. So if you recall your geometry class, this kind of equation in this box describes what's called a conic section. And depending on the particular values of these coefficients a, b, and c, it describes different geometric shapes. The particular scalar value that you can calculate out of this formula, it's called a discriminant, which is equal to b squared minus 4 times ac, will tell us what the shape will look like, as it turns out. So if the discriminant is a negative number, what you're looking at is an ellipse in this two-dimensional space of x and y. If it is perfectly equal to 0, what you're looking at is a parabola. Or if it is positive, then what you're looking at is a hyperbola. So here are some examples. Here's a conic section. And if you calculate its determinant, you will see that it is actually discriminant. It is actually equal to 0, that delta. And if you plotted that, of course, it will look like a parabola in the xy plane. Here's an elliptic conic section. Its discriminant is negative 32. And here's a hyperbolic section. The blue lines, the blue curves. Its discriminant is a positive number. Now we're going to utilize the same sort of naming convention for our partial differential equations. In particular, if our partial differential equation is written down to look like this, where the partial derivative of u, second partial derivative of u with respect to x is being multiplied by a, the cross derivative is multiplied by b, and the second derivative with respect to y of our field variable u is multiplied by c, and then the right-hand side is our driving function in general of x and y, of u, of the partials of u and with respect to x and y. Then we can calculate the discriminant for this function, just like we did for the conic sections in geometry, and then call our PDE either elliptic, parabolic, or hyperbolic PDE. So this is a naming convention that tells us something about the character of the PDEs that we're solving actually. This does not suggest the shape of the solutions or the field variable or anything like that. It just tells us about something about the character of these ODEs. And it's easy to remember if you remember your lesson from geometry, so that's all there is to it. So it's just a name But it is important for us to know whether the PDE is a parabolic elliptic or a hyperbolic PDE, because they display different character, and then different solution methods are matched to those characters. So it's important to classify them. So here are some archetype equations from each category. The wave equation here, it describes the waves, and for example, this one describes the waves, mechanical waves in a solid medium, like a one-dimensional rod, transmitting pressure waves or shear waves, or a vibrating string. And if you evaluate its discriminant, you're going to see that it's going to be a hyperbolic equation. It's a positive number as given. And there are physical meanings attached to, for example, this A, but we'll talk about that later when we talk specifically about the wave equation, what its physical meaning is and what it describes, etc. Here's the heat equation. It is a parabolic one. Its discriminant is equal to 0. And then here is the Poisson equation. It's an elliptic equation, and its discriminant is a negative discriminant. It usually describes a potential field. For example, if you have a porous medium and you saturate it with water and you apply pressure sources at certain locations, and you ask yourself, well, what is the pressure at any given location? Well, then you will determine that by solving this equation. We'll talk more in detail about each of these equations, and we're actually going to attempt to solve these equations numerically for different kinds of domains. As you can see, the wave equation involves a time variable and a space variable. The heat equation also involves the same time and space, whereas the Poisson equation here in this case involves only spatial coordinates, x and y. So let's go back to the wave equation. What does it do? Well, as I mentioned to you, it describes the pressure. It describes the mechanical waves, for example, propagating in a solid medium. This animation you're looking at could very well be the pressure in a rod that is impacted by a hammer at one of its ends, and so this pressure wave is transmitted to the left and to the right and gets reflected on both ends, and it's a perpetual motion. Hyperbolic PDEs in general, and this wave equation in particular, is describing a time-dependent but conservative physical process, right? So you see this wave going back and forth, so we see variation in time, but we see no damping in here. There's no dissipation of energy. It is a conservative physical process. And even if there was damping, it would obey the laws of thermodynamics, basically. And in this particular case, the solution is not evolving towards a static state. It is a perpetual motion. You may see the pattern repeating itself, but it is not becoming a static solution. In fact, I kind of misspoke earlier. If you actually had a damping term, it would change the character of this equation from being hyperbolic into something else. I think that would be, in this case, a parabolic equation, and then that would evolve into a static state. So here's the heat equation, case in point. It's a parabolic equation, and it describes, again, a time-dependent, but this time dissipative physical process. So there's dissipation in here, and ultimately, whatever initial condition that you're given, this evolves toward a static state and a steady state. You can think of this problem as like a steel plate. Just imagine this animation. A steel plate that conducts heat, and on that steel plate you put some iron, hot iron, and it just elevates the temperature where it's at, and then obviously over time that temperature is going to diffuse into the interior of the plate and gets distributed. And it may even be dissipated by its interaction with other objects that are attached to it. Those will be the heat sinks. Okay, so that's a parabolic PDE. Finally, here's here's our elliptic PDE. It describes a time-independent physical process that has already reached steady state. So when I mentioned to you earlier about the porous medium that is saturated with water and pressurized at certain locations, I meant this Poisson equation to describe the solution after all the transients have taken place and ended, and then the solution has reached a steady state. And this equation in the blue box describes that solution at the steady state. So this, is, if you will, is the pressure distribution inside a porous medium. And then let's say that this is some well or a pipe that is generating some water pressure into that porous medium. And then a certain time has already passed, and then this solution has reached that steady state, and this pressure distribution has stabilized. And this blue box, this equation inside the blue box, is precisely describing that final solution. So if we solve this equation, given our boundary conditions, we will end up with that solution. And we will know what that steady state is, but nothing in between. Nothing from the initial time to how this thing has evolved. Okay, so solution methods for PDEs are just basically under two categories. One category is analytic solutions, and there are many angles of attack, and they are devised for different PDEs. For example, method of characteristics was something we've described. You can also utilize series solutions, separation of variables, etc. But of course, not all PDEs will allow you to obtain an analytical solution because maybe the driving function itself is very complicated. Or more typically, your domain is an irregular domain. Your boundary conditions are very complex, and therefore an analytical solution is not at all possible. In which case you would resort to discrete methods, numerical methods, which is the subject matter of our course. And in the context of civil engineering, we have, for example, the finite volume and finite element methods. Finite volume methods are typically used in civil engineering for fluid mechanics problems, and finite element methods are typically used for solid mechanics problems. And a complex domain such as this tire rim, for example, if we're interested in figuring out its stress distribution given the loads on it, is divided into small domains. And the idea of the finite element methods is, and these little small domains are called finite elements. And the idea of these having these small domains is that even if the solution is irregular and very complicated in the whole domain, if you focus on a small region of this domain, a tiny little portion of it, a tiny finite element portion of it, the solution there will be more or less regular. So we can use lower order functions to approximate the solutions over this little domain, which is non-overlapping with other domains, and then hope to obtain a good approximation. And of course, the accuracy of our approximations can hopefully be controlled by controlling the size of our finite elements. That will be mesh refinement, or increasing the order of the interpolating functions within each finite element of our field variable, and that will be the polynomial refinement. And those kinds of things will be offered to you in courses later on, in a finite element analysis course or a finite volumes course on fluid mechanics. There are other techniques such as mesh-free methods, which we use in our research in our department, for example, where we use low-order approximating functions on small but overlapping regions of the domain, and it gives us certain advantages to do this, especially for large deformation problems and problems involving fracture and fragmentation. Here's an example from our own research here at UCLA. This is a reinforced concrete slab which is attacked by a high velocity projectile, and it's punching through it, and this mesh-free method that we use is allowing us to determine how it gets damaged, the size of the hole, where the fragments fly, etc. So this is a very complex problem for which an analytical solution is impossible. And these discrete methods, in particular the mesh-free method, allows us to actually calculate those things with high fidelity using physics principles. There's also another large class of methods which has many common features with these other two sets of techniques, and it's the finite differences techniques, and we're going to actually cover those now in our class. So that concludes the first part of our presentation.